Now let's say I want to draw the magnetic field between two bar magnets with opposite poles facing each other. So north, south, north, south. Well, we know that opposites attract. So what we're showing here is two bar magnets with opposite poles facing one another. In other words, they are attracting. Okay, so we're just going to draw this. So first of all, we know that when we're drawing magnetic field lines external to the magnet, we are going to draw them from north to south. And internal to the magnet, remember we need to complete that loop, we're going from south to north. External to the magnet, we're going north to south. Internal to the magnet, south to north. And now we have completed that first magnetic field line. So this is what I was saying before, where when you have the opposite poles facing each other, you have the same polarity shared by both of these magnets. In other words, the same directionality of electron spin. And that is why they are attracting. Okay, so let's draw our next line. So external to the magnet, away from north, towards south. So there's the first part of our loop. Internal to the magnet, so inside of this bar magnet, south to north. Outside of the magnet, north to south, right? This is attracting to this. Internal to the magnet, south to north, and now we've completed that loop. And this is an example of a diagram depicting the magnetic field between two magnets who have opposite poles facing each other. We could create an abstraction of this image and just isolate the south and north pole. This is just as though we were only to look at the inside of this situation and omit out the other two poles. We know that monopole magnets cannot exist. So this is just an abstraction of this, and one way we could depict it is like such, north to south, north to south. So this is another acceptable way of depicting this in an abstraction. But one of the rules that you'll remember from drawing electric field lines is that these field lines should never intersect each other. They should never overlap. So make a note to yourself. Remember, field lines should never overlap or intersect. Now, if we were to flip this situation around and have north on this side and south on this side, remember that we always are going external to the magnets from north to south. So north to south, north to south, north to south, north to south. Okay? And it's just like in electric field diagrams, in magnetic field diagrams, wherever the field lines are closest together, the magnetic field is the strongest. So also, where field lines are closest together, magnetic field is the strongest. And we know that the further you get away from these magnets, the weaker that magnetic field strength will be. Okay, so now I want to look at the opposite situation where we have two bar magnets with like poles facing each other. So two bar magnets with like poles facing. In other words, these are going to be repelling. So I'm going to do, let's just do north and north. So let's go north, south, and same thing, north, south. So now we have two like poles that are facing each other, and we know these are going to repel each other. So what this looks like is it almost looks like two freely floating bar magnets. So you have north to south, external to the magnet, and then south to north, internal to the magnet. Sorry. Okay. So north to south, external to the magnet, south to north, internal. Same thing on the bottom, north to south, external to the magnet, and south to north, internal to the magnet. Okay, now I'm going to do the same thing over here, and this is going to be north to south, external, north to south, external, and south to north, internal, south to north, internal. Okay, so when you create an abstraction of this, it's actually going to remind you a lot of the electrostatics unit. So if we look at this, north and north, we just isolate those two poles. What you end up with is something that looks very similarly to when we had two protons repelling each other. Just like that. So that would be our abstraction. Okay, so now let's do the same thing, but this time with two south poles facing each other. So let's do south and north, south and north. So we're going to draw the magnetic field lines over here. Again, external to the magnet, it's from north to south, like this. Internal to the magnet, it is south to north, like that. External to the magnet, it's north to south. Internal to the magnet, it's south to north. Okay, same thing over here. External, it's north to south, north to south, internal to the magnet, south to north, south to north, just like that. And if we create an abstraction of this, these two repelling magnets, let's just look at the south and the south. And this is going to remind you a lot of when you would have had two electrons or two negative charges repelling each other, where your field diagram will look something like this. Okay. So the other point that I want to make is, if you've ever used a compass to figure out where you are or which way you're traveling, again, just remember the way a compass works. A compass has a freely floating bar magnet with a north pole and a south pole, and this north pole is supposed to tell us which way on Earth, this is used to tell us which way is due north. Right? But this is actually confusing because if the North Pole on our compass is attracting to the North Pole of Earth, right? So geographic North Pole. How is north on the compass attracting to north on Earth? If we know that like poles are supposed to be repelling each other. Well, I just want to make it a point to say to you that actually the north on your compass is attracting to geographic north because geographic north is actually magnetic south. And that is how the North Pole on your compass can attract to geographic north, even though they appear to be like poles. They aren't. The North Pole, geographically, is actually magnetic south, which means that the geographic South Pole is magnetic north.